Okay, so this is a question 2. Now we're going to solve this problem. So you can see we have two types of gasolines, and they're blended by passing through a horizontal way. This is a Y shape. You can see we have defined this name. This is section 1, 2 and 3. So this is the total schematic. We know the flow rate for this section. We know the flow rate for this. You can see this is 3.4, and we don't know the flow rate for this one. So definitely you know the you know the continuity equations, and the mass flow through this inlet, it should be equal to the mass flow through this outlet. So that's the the mass conservation principle and the equation of continuity. We know the diameter of this section. 100 millimeter. We know the diameter of this section. This is the center line. We actually need to calculate the magnitude and the direction. The same thing like what we did previously, but here you see the magnitude and the direction of the force exerted on the V by the gasoline. That you need to keep in mind. The force exerted on the V by the gasoline. So that's actually we need to calculate. So if you see, this is the center line, and this is actually the the in light of the section 1, this is the flow directions for section 2. So what happens is it creates a 30-degree angle here, and this one creates a 45-degree angle here. So it creates a 45-degree angle here. So that's the two angle, and you see this is section 1, section 2, section 3. So what I say, this is really important because when the direction changes. So if we consider this total system is like this, let's say this is X and this is Y. So this is X direction, this is Y direction. So you can see when we are considering this way, so this is creating a 30 and 45-degree angle. So definitely this is the change of angle in the direction. So we need to consider both the X and Y component of the velocity and the force, pressure force. So let's solve this problem now. Okay, first we need to understand what is happening here. Look at this figure. You may find this is a little bit busy, but you see this is section 1. We know the diameter. The velocity for this section 1 is p1. Okay, and the pressure here, the area is a1. So if we know the area and if we know the velocity, so the pressure here, it is p1. We know the velocity is b1 and area is a1. So due to the pressure, we have a pressure force like p1 a1. Force equal pressure into area. So we know the area a1 and we know the pressure p1. Similarly, let's say the velocity for this section 2, we will define this as v2, area is a2, and the pressure is p2. Okay, so then we have the pressure force p2 a2 here. So now let's say the velocity is v3 here, the area is a3. Okay, so the area is a3, so the pressure is p3 a3. Let's see, we say this is the x direction, this is the y directions. The gasolines coming through this way, and this inlet and this inlet, they are meeting here. So this is the x-axis. So you can see we have the force component fx this way, and this is the the resultant fy force. This is the force along x direction, this is the force along y directions. So now the important part is what is happening. You see this direction, this is the flow. You see the flow rate, so it is coming this way. So if I draw this, so let's say it is, look here, so it's something like this. It is coming this way. This is actually the velocity v1. Okay, so this is the velocity v1. I will use the other color. So let's say this is the velocity v1. Yeah, so this is v1. It is coming this way and it creates an angle. You see, 30-degree angle here. So definitely this is, the velocity, the one, you see, this is the x-axis, isn't it? This is x-axis, and if we draw another line, so this is the y-axis. So look here what I did. So this is the velocity here. Yeah, so see, this is the velocity v1, and this is the 30-degree angle it creates here. We have one more. This is the y-axis. So that means this velocity is going this way. This velocity, it is the directions, because this is the velocity direction. So this x and y component, it will be in the same directions, like x and x. So when it is along the x-axis, the horizontal axis, so it should be b1 cos 30. You see here, it should be the b1 cos 30, and for the horizontal axis, this is b1 sin 30. I think it's clear now. Similarly, we have the pressure force. The pressure force acting this way, P1 A1. So that means I'm talking about this section 1. So we have this pressure force P1 A1. It is acting this way. So this is P1 A1. This is the x-axis. You see, 30-degree angle here, and this is the y-axis. So as the x-axis is the horizontal axis, so it should be this pressure force P on A1 cos 30, and this is P on A1 sin 30. Make sure that you have the P on A1 in these directions, so it should be, this force and along this x-axis and this force along this y-axis, they will meet. Their direction will be the same. So this is for section 1. Now if I enlarge this section 2, so you see the velocity is going this way. Let's say this is our velocity. You see, it's going this way. So if I increase this line, something like that, so it creates this 45-degree angle here. So you see, it's creating 45-degree angle here. So this is our x-axis, and this is the y-axis. Look, in this case, y-axis is not here because this velocity is going this way, so you need to divide this velocity along the x and y. So it's not acting this way, it is acting this way and this way. You see these directions. So as this is the horizontal surface, so v2, it is 45-degree. So v2 cos 40, this is v2 sin 45. Okay, cos 45 sin 45. Similarly, let's say instead of the velocity, the pressure force is acting there. So sorry, it should be here. It is creating the 45-degree angle here. Okay, so when it is the pressure force P2A2 in this way, so similarly for the horizontal axis, P2A2 cos 45, P2A2 sin 45. Right? Do we have any angle here? No. So that means only the force and the velocity and the pressure, we have only along the x-axis, not y-axis, so nothing along y-axis. So I believe now it's clear. Actually, you need to draw this at the very beginning when you will solve this problem. So you need to understand actually how to distribute the force and the velocity along the x and y axis. So now we will start with the solution. So I will show you some simple calculation now. At section 1, we know the mass flow rate is 30. You see, this is 30. So we need to calculate the velocity, because you can see how we just calculated those force and the pressure force and the velocity along the x and y axis. So from the flow rate, okay, we will calculate the velocity. So that means we need to divide by using the area. So pi by 4 d square. So for section 1, this is, we said velocity v1. You see this is 30 liter per second, and this is pi by 4. Diameter is 200 millimeters, so that means 0.2 meter. So in that way we'll calculate for v2. You see the same thing. We have 3.4 liter per second, so just convert it into the meter cube per second, and this is the area. You see diameter is 100 millimeters, so 0.1. Similarly for v3 we calculated the velocity. So we calculated the velocity for section 1, section 2, section 3. But the important thing here, you see, when it is v3 we don't know any mass flow rate, but this 30 liter per second, this 3.4 liter per second, they're coming this way from a bifurcating tube, and they're merging, they're meeting this section. So we will have, according to the the continuity equations, the conservation of mass principle, the flow rate here, it should be the sum of these two. So that means this is 0.03 and this is 0.0034. So in that way we calculated the v3 here. Now we will calculate the force, so along the x-axis, if we consider the control volume, so along the x-axis, the net force Fx, this is equal, the momentum principle. You already know, we used this formula for previous problem. So the Fx is rho Vx v dot A. So how many forces we have along the x-axis? So let's calculate the net force Fx at the very beginning. So you can see along the x-axis, for this section 1, we have one force. This is the pressure force P1A1 cos 30. So this is in the positive x-axis. So you see P1A1 cos 30. Similarly, we have, you see, P2A2 cos 45. For this section 2, you see this is the pressure force P2A2 cos 45. For section 3, we have the pressure force is P3A3. So it should be negative because it is the opposite direction. This force is coming this way, pressure force this way. So according to the the theory, this P3A3, it will go through the opposite directions. So that's why it is negative here. And we have one more force, the resultant force. This is Fx. You see, it is in the positive x directions. So this is Fx. So that's all forces we have along the x-axis. This is the net force along x-axis. Now calculate the moment. So this is the sum of rho Vx v dot A. So if we put this rho out of this, then it should be Vx v dot A. So if you can remember, I said this is the rate of change of moment. So that means I said we will solve every problem by using the same principle, like the final moment minus the initial moment. So the final moment we will get here, and this is for section 1, section 2, it will be initial moment. So let's calculate for section 3. So for section 3, it creates a 0 degree angle. That means no 30, 45. So cos 0 degree, this is actually, it means 1. So it creates a 0 degree angle. So that means our velocity, the Vx, it should be only v3, not. So you see, for other two section 1 and 2, we have v2 cos 45, sin 45 this way, but section 3 we have no change of directions, no angle, so it should be only v3. And you see, this is the dot product we already explained, so v3a3. Now this is the final moment. I said you will calculate the moment difference, so the final moment minus the initial moment. So this is the minus. Let's calculate for section 1. So for section 1, we need the velocity along x-axis. What is the velocity? You see b1 cos 30. So this is b1 cos 30. This is the velocity, and it should be b1 a1. Similarly, the negative sign, because calculating the difference between the final and the initial moment. So for this section 2, so this is the drawing for section 2. This is, you see, the x component, velocity component, b2 cos 45. So say b2 cos 45 and b2 8. This is quite simple. I can make it very complex, but I'm trying to make it simple that you can, if you follow this method, you can solve any problem from this chapter. So now let's say we need actually we need to calculate. We don't know the pressure, so we need to calculate the pressure. And now we will start solving. We will implement the Bernoulli principle. Okay, so if we implement the Bernoulli principle, you see here, we need to know if we want to calculate this net force. You see the P1, P2, and P3, the pressure. We don't know the value of P1, P2, P3. So what we can do is we can implement the Bernoulli principle here. So for 1 to 3 or 2 to 3, in that way we can calculate, we can get the pressure. We know the pressure P3, it is given in the question. You see the pressure P3, it is given 145 kPa. So this is given. So now what we will do is we will implement the Bernoulli principle for this section A and section 1 and section 2. So the Bernoulli principle, it is P on rho z, V on squared 2g, z on, this is the elevation, P3 rho z, P on squared 2g, and z3. So let's say this is in the same elevation. And now if we substitute the other value, we don't know P1, but we know the density and the gravity. We know the velocity, we calculated it. We know V3 and we know P3. So if we substitute all of these values, then we will get P1. So yeah, just simplify these equations, use your calculator. This is very simple. So you see we got P1. Now we will implement the Bernoulli principle for P2 and P3. So if we implement the Bernoulli principle for P2, P3, it's the same thing. P2 rho z, V2 squared 2g, Z2, P3 rho z, V3 squared 2g, and Z3. So we consider this the same elevation. Substitute the other values. So now you know P3, but we don't know P2. So if we substitute all other values, then we will get the P2. So this is P2, we got it from this calculation. So once we know P1, P2, we already know P3. So if we substitute everything, then we will get an expression for the net, the force along x-axis. Right, so you see the net force is this. We substitute all values P1, A1, everything, then we got this. The net force equal Fx plus 199.4. So now according to the formula, we need to calculate this. So if you see this is we got the draw Vx v dot a equal this, right? So we need to just substitute each and every value to get this one. So this is the term here. You see this rho v3a3 minus v1 cos 30. So this is the term. So if we substitute every value here, so we know v3, v1, we know the area a1, a2, everything. We know the density of gasoline 680. So if we substitute every value, then we will get an expression for this. Right. So look here. We simplified this and we got this is 6.5 Newton. So according to the momentum principle, the net force, it will be the rate of change of the momentum. So we got the net force is Fx plus 199.4. It is equal to the 6.5 Newton. So yeah, Fx equal this. So this is, we got the Fx equal negative 193 Newton. So that means this is the directions. If you see the figure, you can see Fx, it is this way. So we got the negative, that means it is in the opposite directions. So look here, this is, we got the Fx like 193 Newton. So this is the opposite directions. So now we need to calculate the force along y-axis. the force along y-axis, it should be pretty much easier because this is not that complicated. If I show you the figure, so the along y-axis is the sum of Fy and rho. Instead of Vx, it is Vy. So rho Vy V dot A. The Fy, sum of Fy, it is, look, how many forces we have along the y-axis. So this is actually, for this section 1, we have the force, we have the force P1 A1 sine 30. P1 A1 sine 30. This is going to the downward directions, but the Fy is upward direction. This is the positive, but this force, it is acting along the y directions, but you see this is the negative, so it should be negative P1 A1 sine 30. So you can see negative P1 A1 sine 30. So this is for P2 A2, that means this is for section 2. Let's check for section 2. This is for section 2. You see this is the force, it is acting this way. This is the positive y direction, so plus P2 A2 sine 45. So you see plus P2 A2 sine 45 and Fy. So the Fy is this force. We have no force at section 3. So if you see here, we wrote this, all of these forces. We know pressure P1, P2, P3. We know area. So just substitute every value, simplify it, then you will get the values Fy minus 1472. So that's the net force along y-axis. So now we will calculate the rate of change of moment. Right. So what I said, now we will calculate this, the right hand side. So this is rho Vy V dot A. So we can put rho here, and then it will be the Vy V dot A. So look, can you remember what I said earlier? I said this is actually the rate of change of moment. So you need to calculate the final moment minus the initial moment. So if you see here, what is your final moment? So the final moment means the moment here at section 3. Do we have any velocity here along y-axis? No. So it will be 0. So that's why you can see this is 0. Now we will calculate for section 1. So we say this is the V1 along y direction, V1 A1, and V2 along y direction, V2 A2. So what is V1 y? So you see the V1, the velocity along y direction is V1 sine theta, sine 30. It is going to the opposite directions. This is y-axis, it is going to the opposite direction, so it is negative V1 sine 30. It should be negative V1 sine 30. So you see, this is the minus, this is for formula, but we have negative V1 sine 30 and V1 A1, and minus, what is V2y? So look here again, the V2y, so it is acting this way, so this is the positive y direction, so V2 sine 45. So if you look here, this is V2 sine 45 and V2 A2. So now just substitute all the value V1 A1 V2 A2, then you will get it is 9 Newton. So that means we got the net force along y direction is Fy minus this, and I got this is 9 Newton. So this equal this, calculated, you get Fy equal 1481 Newton. This is positive, that means it is the positive y directions. You see, it's the positive y directions. Now what is the magnitude? Just the square root of fx square Fy square. So you got 1494 Newton. So that's the magnitude. So now we will calculate the direction. This section is very important. We are going to calculate. So look guys, we got the force along x-axis is 193. This is the directions. Force along the y-axis is this. This is the directions. Hence, the force by fluid one way is reverse of that by way of fluid. That means if you can remember the previous problem, what is said according to the Newton's third law of motion, every action has an equal and opposite reactions. See, we got this fx equal this, so we will have a similar, equal fx along this axis, and similarly for fy along this axis. So if we, just draw the plot here, let's see how it looks like. Yeah, so if you see here, you can see this is the apex. We draw this line, apex is this, and this is the fy. This is actually the force F. When we solved the other problem, we found it creates the angle theta here. But here in this problem, I said, okay, it is creating the angle here. So maybe you can see the problem. So let's have a look. So see here, we need to calculate the direction of the force exerted on the V by the gasoline. You can see this is the center line. It is creating the angle with this horizontal axis. If we go back to that figure here, you can see this is actually the horizontal axis. So it creates that angle theta here. So now when it creates this angle theta, so we know tan theta equal fy fx, right? So here, when it creates the angle this way, so it will be, so for this case the fy it is 1481 and fx is 193. So if we calculate the angle, it should be 82.6. So just see the other video like for the first problem, and then you will see the difference, like how to calculate the directions. So you need to be careful with these directions when you are going to calculate the angles. So that's the second problem.